Okay, let's unpack this. Imagine you're gearing up for a high-stakes DevOps interview, right?
Hmm.
And the interviewer leans in, maybe with a bit of challenge in their voice, and asks, how do you handle a monolithic, sprawling Terraform state file, say one that's whopping 4 gigabytes?
Yeah, that's a classic.
That's the core of our deep dive today. And look, this isn't just some theoretical thing you read about. It's a real, often painful challenge that can genuinely paralyze your infrastructure management.
Oh, absolutely. A 4 gig state file.
Yeah.
It's more than just big. It's a genuine nightmare scenario. It usually points to an infrastructure with like over 2,000 resources, just vast interconnected systems.
Wow.
And the operational pain, it's immediate, it's severe, it can grind everything to a halt. But here's the good news, and this is what we'll really dig into today. There's a solid, proven strategy for this.
Oh.
It's all about systematically breaking down that monster state into smaller, much more manageable microstates. And this isn't just, tidying up. It's fundamental. It boosts your team's agility, massively improves reliability. So yeah, this deep dive, it's designed to give you that structured, confident answer for exactly that interview question.
So let's really paint a picture of this 4GB state file problem. When we say monolithic infrastructure management nightmare, what does that actually feel like for the engineers day to day? Are we talking thousands of resources, multiple environments, different services, maybe even separate teams, all tangled up?
Precisely. Yeah, it's not just the file size itself.
Yeah.
It's the deep systemic problems it creates. From what we see out there, the direct pain points are pretty stark. You're looking at Terraform plan times stretching to 30 minutes.
Or more.
30 minutes.
Yeah.
I mean, imagine kicking off a plan, going for coffee, coming back,
Yeah.
still running. It just crushes developer productivity.
Yeah, I bet.
Then there's the constant fight with state lock contention. You've got multiple engineers, maybe CI/CD pipelines, all trying to tweak infrastructure managed by that one giant state file. They're constantly stepping on each other's toes.
Yeah.
It leads to frustrating bottlenecks, just wasted time.
Oh.
And maybe the scariest part, the blast radius. A single, seemingly tiny mistake, a misconfiguration, an accidental Terraform destroy command on that one massive state.
Yeah.
It could potentially impact your entire infrastructure.
Yeah, that's terrifying.
If you've ever felt that pit-of-the-stomach dread hitting enter on Terraform plan with a huge code base,
Yeah.
you know exactly what we mean. The stakes are just incredibly high.
That dread is so real. I've definitely felt that. Okay, so that's the problem laid bare. What's the escape route? How do you even start untangling something that complex, that interconnected, without, making things even worse?
Right, yeah, because you can definitely make it worse if you're not careful. This is where you need a really strategic architectural approach.
Hmm.
The critical first step, and honestly, it's one people often skip in the rush, is what we call resource boundary analysis.
Okay, resource boundary analysis.
Before you even think about moving a single resource,
Yeah.
you've got to systematically categorize your entire infrastructure. The way we typically do this is first get a full list of everything Terraform manages. You can run Terraform State list, maybe pipe that output to a file.
Right.
Then you start grouping these resources conceptually. Like, okay, let's find all the networking stuff, VPCs, subnets, route tables. Use grep or similar tools on that file. Then find all the compute EC2 instances, auto-scaling groups. Same for databases, RDS, so Elasticache, whatever you have.
So grep os VPC os subnet for networking, maybe grep os instance for compute, something like that.
Exactly. You basically build this methodical inventory. It gives you a really clear picture of what you actually have, which makes dividing it up way less daunting.
That makes total sense. It's like trying to untangle a giant knot without even seeing where the threads are. Are there common, pitfalls people hit during this analysis? Things they often miss?
Oh yeah, good question. A really common one is just rushing it or trying to guess based on assumptions. You need to be exhaustive.
Hmm.
Another thing is not thinking about the future growth. Team changes during this analysis. But assuming you've got that solid categorization, the next bit is defining the optimal boundaries for these new microstates. We've found a few key principles really help guide this separation.
Okay, principles.
First, and this is critical, blast radius isolation. You absolutely want to separate your super critical stuff like core databases from things that change more often or are less critical, like maybe some compute services. The whole idea is if a compute change goes wrong, it doesn't take your databases down with it.
Right, contain the damage.
Exactly. Second, team ownership alignment. This is huge. Ideally, each microstate should map clearly to a single team that owns and manages it. This clarifies who's responsible, empowers the teams, and cuts down dramatically on that cross-team coordination mess you get with monoliths.
Makes sense.
Third, try to aim for dependency minimization. The fewer times one state has to reach into another state for information, the simpler the whole system is. Lots of cross-state dependencies can kind of bring back some of the problems you were trying to fix.
Okay. Keep it clean.
Yep. And finally, think about change frequency grouping. Stuff that hardly ever changes, like your core network setup. Keep that separate from dynamic things, like compute instances that scale up and down or get deployed multiple times a day. It just means you touch the stable states less often.
All right, so we've defined the boundaries based on these principles. Now, how do we physically separate them? Is it just moving Terraform files into different folders, or is there more to it?
It's definitely more sophisticated than just moving .tf files around. It's about setting up what we call a multi-state backend strategy.
Okay.
This basically means creating completely isolated backend configurations for each new microstate. So let's say you use S3 for your backend, which is common. You'd configure one S3 backend block specifically for your networking microstate and a separate one for your compute microstate.
Ah, okay.
Now, they might actually use the same S3 bucket, maybe even the same DynamoDB table for locking. That's fine. But the crucial part is the key parameter within each backend configuration.
The path inside the bucket.
Exactly. You'd have something like networking terraform.tfstate for one and compute terraform.tstate for the other. That unique key ensures each microstate gets its own distinct state file within that bucket. They're truly isolated, managed independently, even if they share some underlying backend infra.
Okay, here's where it gets really interesting. And honestly, where I think a lot of the fear comes in for engineers. The practical steps for a zero downtime migration. How on earth do you pull this off without breaking production? Because that's the ultimate nightmare.
It absolutely is. And this is, without doubt, the most critical phase. It demands a very methodical, step-by-step approach. No shortcuts here.
Lay it on us. Phase one.
Phase one. State file preparation and backup. This is absolutely non-negotiable. Before you touch anything, you need a bulletproof backup strategy.
Okay, backup first. Always.
Always. This isn't just good practice, it's your critical safety net. So you use a command like Terraform State Pull to get a fresh, perfect copy of your current monolithic state file. Say with a timestamp like monolithic backup, date plus percentage h%.ts.tf state.
Got it.
And then immediately copy that backup somewhere safe, somewhere durable. An S3 bucket dedicated to backups is a good idea. S3 TP that file right over. And the emphasis here is on multiple copies, maybe different storage systems, different regions even.
Why multiple?
Paranoid. Healthily paranoid. Because state corruption during a migration, while rare, is catastrophic. It could make your infrastructure basically unmanageable. Having those robust, redundant backups is your oh crap button if things go sideways. It's your rollback plan.
Okay, backup secured. What's phase two?
Phase two. Resource migration. Using Terraform State MV, this command, this is the absolute backbone of doing this without downtime.
State MV. Got it.
And it's vital, really vital to understand how it's different from Terraform State MV. Terraform just tells Terraform to forget about a resource. It orphans it. The actual thing in the cloud is still there, but Terraform isn't managing it anymore.
Right, which could be bad later.
Exactly.
Yeah.
State MV, on the other hand, it transfers the management of a resource from one state file to another while leaving the actual infrastructure completely untouched. You're not destroying anything. You're just telling Terraform, hey, this resource is now managed over here.
Ah, okay. Changing its address in Terraform's world.
Precisely. So the professional pattern here is pull down your current monolithic state, source.tf state. Create new directories for your target microstates, mkdir-p, networking, compute, database, monitoring, whatever they are. Initialize Terraform in each of those new directories, pointing them to their new isolated backends.
Right.
Then you start moving resources. And you want to do this thoughtfully, often batching by type or logical group to avoid breaking dependencies. You might use Terraform state list-state.source.tstate piped to grep again to find, say, all your VPC and subnet resources. Then you could use something like zargs to feed those resource addresses to Terraform state MV, specifying the source state and the target resource address in the new state.
So like Terraform state, mv-state.source.tf state, audusvpc.main, audusvpc.main.
Right.
Moving it to the currently initialized directory.
Exactly. Or you might move specific instances like osavnet.private data. The key is moving related groups together. Move the VPC stuff to the networking state before you move the EC2 instances that live in that VPC to the compute state.
Okay, moving resources carefully. What's phase three? This feels like the magic part.
It kind of is. Phase three. Moved block implementation for state tracking. This is the critical piece that actually guarantees zero downtime during the cutover.
The moved block, okay.
So what the move block does, it sits in your Terraform configuration files in the new microstate directory. And it essentially tells Terraform, hey, you know that resource you're expecting to create at this address? Well, it actually already exists because it used to live over there in the old state.
Like a forwarding address.
Exactly like a forwarding address, just like telling the post office where you move. It prevents Terraform, on the first apply in the new state, from saying, oh, I don't see os vpc.main, I must need to create it. And also prevents the old state, if it were still active, from thinking it needs to destroy it. This block bridges the gap, telling Terraform to just adopt the existing resource at its new address.
That's clever.
It is. You'd have blocks like move from oscvc.legacy.main to oscvc.main. It also works for count-based resources, mapping old indexes to new ones, like from osubnet.legacy.private to osubnet.private-era.
Okay, crucial detail time.
The absolutely critical insight here is that move blocks are temporary. They are migration tools only. You must remove them after the very first successful Terraform apply runs cleanly in each new microstate.
Why remove them?
Because if you leave them in, they can mask configuration drift later on or cause really confusing behavior if you try to rename or refactor things again. They serve their purpose for that initial adoption, then they need to go to keep your config clean and accurate.
That is incredibly smart. A temporary redirect just for Terraform itself. What a lifesaver. Okay, so resources are moved. Moved blocks prevent destruction on first apply. But what about those dependencies between the states now? If my compute state needs, say, a subnet ID from the networking state, how do they talk to each other across these separate universes?
Excellent question. That's where the dependency resolution strategy comes in, and the tool for the job is the data Terraform remote state data source.
Terraform remote state, okay.
Yeah. Instead of trying to directly reference resources across state boundaries, which you just can't do, this data source lets one microstate securely read the output values from another microstate state file.
Ah, outputs.
Exactly. So in your compute main.tf, you define a data Terraform remote state block. Let's call it networking. You configure it to point to the S3 backend where your networking state lives.
Right.
Then, anywhere in your compute configuration where you need, say, a private subnet ID, you'd reference it like data.terraformremotestate.networking.outputs.private subnetted 0. You define explicit outputs in your networking state, like the subnet IDs, and other states can consume them via this data source. It's clean, it's explicit, it keeps the states decoupled, but allows controlled communication.
That's a really elegant way to handle it. Much more modular. Now, thinking bigger picture. Enterprise scale. Thousands of resources, maybe dozens of teams. Doing all this state MV and move block generation manually, even with scripting, it still seems daunting. Is there tooling to help automate some of this complexity?
Absolutely. For those really large-scale scenarios, looking into automated migration tooling is often a good idea. While Terraform State MV is fundamental, you're right, doing it thousands of times is prone to error and just tedious.
Yeah.
There are tools out there like Terraform State Split is one example people mention. These tools can often provide more interactive ways to select which resources go where, maybe visualize dependencies to help you make better boundary decisions, and critically, they can sometimes auto-generate the necessary state MEV commands and even the corresponding move blocks from low.
Oh, nice.
Yeah, it can significantly cut down on the manual work and, importantly, reduce the chance of human error, which is always a risk in complex migrations.
Okay, so we've done the analysis, the careful migration, used the move blocks, handled dependencies, we're almost there. But how do we really know our new microstates are production ready before we, pop the champagne and delete the old monolith backup? What's that final sign-off?
That's where you need a solid, production-ready implementation framework. It's got a few key parts. First, a comprehensive validation and testing strategy. This is non-negotiable before declaring victory.
Right, test.
Exactly. You need to validate each microstate independently. A good practice is to loop through each new state directory and run Terraform plan detailed exit code.
Detailed exit code, what does that do?
It makes Terraform Planner return a specific exit code if it detects any changes are needed. 0 means no changes, 2 means changes are pending. So you script this. If any state shows pending changes, exit code 2, something's wrong. You must investigate and fix it before going live. It ensures no nasty surprises.
Okay, plan checks, clean. What else?
Second, you need that instant rollback strategy we talked about with backups, but you need to have practiced it, or at least be absolutely clear on the steps. If disaster strikes during or immediately after the cutover, you need to be able to revert fast.
Back to the monolith.
Back to the known good monolithic backup. That procedure is Terraform State, push your time-stamped backup file back to the original S3 backend location, overwriting the potentially corrupted state. Then run Terraform init migrate state in your old monolithic code directory to force Terraform to reread that restored backend state. It's your emergency eject button.
Got it. Essential safety net. Anything else for production readiness?
And finally, thinking about long-term health. Performance optimization. We've learned some good microstate sizing guidelines from production experience. Generally, aim for microstates with somewhere between, say, 200 to 500 resources. That seems to be a sweet spot for most teams.
Okay. Not too big, not too small.
Right. The goal for developer experience, get those Terraform plan times down to sub 5 minutes. That makes a huge difference. And keep reinforcing that single-team ownership model and minimizing cross-dependencies. These aren't just setup guidelines. They're crucial for maintaining the benefits long-term.
This sounds like a massive undertaking, but you can really see the payoff. So what does life look like after this transformation? How do you maintain this shiny new optimized setup and stop it from slowly creeping back towards being a monolith again?
That's such a critical point. It's not a one-and-done fix. It's a shift in operating model. This is where operational excellence post-migration comes in. You need strong state management governance.
Governance, okay. Like policies.
Exactly. Essential policies like automated backups, think hourly snapshots, maybe to multiple locations. Strict access controls use team-based IAM policies limiting who can touch which state bucket or path. Mandatory change approval use PR reviews for any code change that affects infrastructure state, ensuring peer review. And comprehensive monitoring enable CloudTrail logging for all S3 and DynamoDB actions related to your state, so you have a full audit trail, who did what, when.
Okay, good hygiene. What about deploying changes that span multiple states?
Right, cross-state orchestration. If you need to deploy a change that touches, say, networking and compute depends on networking, you don't just fire off Terraform apply in both directories randomly. No, you need coordination. A simple approach is often a script. It would first run Terraform plan for all the affected states. Check that all plans look good. Then it would run Terraform apply TF plan for each state in the correct dependency order. Networking first, then maybe database, then compute. This ensures predictability.
That makes sense. Plan everything, then apply sequentially based on dependencies. And for bigger companies with dev, staging, prod environments, how does this scale up? Do you just multiply the number of states?
You do, but it's organized. You logically extend the pattern using a clear multi-environment strategy. Typically, you'd see a directory structure reflecting this, maybe Terraform States Prod Networking, Terraform State Staging Compute, Terraform States Dev Database, and so on.
Gotcha. Environment, then microstate.
It's exactly. It keeps environments fully isolated while applying the microstate benefits within each one. And the overall cost and performance impact, the actual benefits you get, are massive. You've seen teams achieve 95% reductions in plan times. Seriously, from 30-plus minutes down to 90 seconds or less per state.
Wow, 95%.
Yeah. It unlocks true parallel team velocity because you eliminate that state lock contention. Teams can deploy their stuff simultaneously. The blast radius containment is huge for stability. A mistake in one area is isolated. And troubleshooting gets way easier because you know exactly which state manages which resources, just by the structure. Honestly, this whole transformation, it's about evolving your operational maturity. It turns infrastructure management from this bottleneck into an actual enabler of development speed.
Okay, so let's boil down this whole deep dive on the 4GB Terraform state problem. What are the absolute key takeaways for you? First, monolithic Terraform states. They're a major drag on speed and reliability. Microstates are the way forward. They're modern, scalable, resilient.
Right. Monolith bad, microstates good. Pretty much. Second, that upfront planning. The resource boundary analysis, it's absolutely essential. Don't skip it. Third, Terraform State MV is your core tool for the move. And using those temporary move blocks correctly is the secret sauce for zero downtime.
Temporary being the key word there.
Absolutely. Fourth, backups, validation, rollback plans. These aren't optional extras. They are non-negotiable for doing this safely and successfully. And finally, making the switch genuinely improves performance, shrinks your blast radius massively, and gives teams more autonomy. It makes your infrastructure work for you, not against you.
So what does all this mean for you listening right now, really understanding this whole life cycle, spotting the problem, designing the solution, the nitty-gritty migration steps, and keeping it healthy afterwards? This knowledge is incredibly valuable, not just for your day job managing infrastructure, but for absolutely nailing those tough DevOps and cloud engineering interview questions about real-world challenges. Knowing this stuff really will set you apart.
And maybe a final thought to leave you with. This raises a really important question. If your infrastructure is still wrestling with monolithic states, what's the actual tangible cost in lost time, in risk, in frustration of not evolving to a microstate architecture for your team's velocity and your system's reliability? That's all for this topic. Stay tuned for the next DevOps Cloud interview question.